A neutron strikes an atomic nucleus and knocks it sideways. Nothing touches the atom's electrons. Yet, in a precise instant, an electron escapes. This reaction is exceptionally rare. Researchers recently recorded nearly 1 million nuclear recoil interactions. Out of that massive dataset, they identified only 6 convincing examples of this specific electron ejection. The mechanism presents a physical paradox. The incoming neutron is electrically neutral. It passes through the atom and strikes the nucleus while entirely avoiding any direct electromagnetic interaction with the surrounding electron cloud. But those 6 microscopic tracks have implications on macroscopic scales. They provide a new mechanism that physicists can use to search for some of the lightest suspected forms of dark matter. Dark matter has never been detected as an individual particle, and its microscopic nature remains unknown. A leading hypothesis suggests it consists of particles that continually pass through Earth, occasionally colliding with ordinary matter. By isolating how a neutral collision forces an untouched electron to escape, physicists can track nuclear impacts that conventional kinematic equations consider completely invisible. Under ordinary conditions, an atom's nucleus and its electron cloud move together. If you apply a gentle acceleration, the entire system adjusts. The nucleus changes motion, the electron probability distributions adapt, and the internal state of the atom remains intact. A violent collision from a fast, electrically neutral particle breaks that cohesion. This diagram visualizes the quantum lag at the center of the event. The nucleus suddenly recoils and shifts its position. But the old electronic wavefunction cannot instantaneously transform into the specific state required for a nucleus moving at that new velocity. To calculate the atom's new state, physicists must express that old wavefunction as a combination of the newly allowed quantum states for the recoiling atom. As this projection shows, the vast majority of the probability still corresponds to the original bound configuration. However, there are extreme outliers. Small components of this data correspond to excited states, and an even smaller, microscopic mathematical fraction places an electron in a fully unbound state. That specific unbound result allows the electron to leave the atom entirely. This is known as the Migdal effect, named after physicist Arkady Migdal, who analyzed atomic ionization during nuclear processes in 1939. A sudden change in nuclear motion forces an internal disruption of the electronic system, triggering an ejection without direct physical impact on the electron itself. This equation defines the kinematics of elastic scattering. The maximum fraction of energy transferred between 2 colliding objects depends strictly on the ratio of their masses. Historically, direct detection experiments were engineered to find dark matter particles with masses comparable to the target nuclei in the detector. If the masses match, the energy transfer is highly efficient. But if a very light particle strikes a heavy nucleus, the light particle simply bounces off, transferring almost no kinetic energy. This creates a severe mass mismatch. If dark matter exists in the lighter mega-electron volt to giga-electron volt range, its collision with a heavy nucleus produces a recoil too faint to cross the detector's baseline threshold. The signal falls into the noise. Because of this mass mismatch, the heavy, multi-ton underground sensor arrays built over the last few decades are effectively blind to low-mass collisions. The impact occurs, but the instruments cannot register the heavy target moving. The Migdal effect circumvents this kinematic limit. If a low-energy nuclear recoil successfully ejects an electron, the detector can stop looking for the faint movement of the heavy nucleus and instead search for the high-energy electronic response. Incorporating this effect into dark matter models required physical experimental proof.
Researchers had to identify the recoiling nucleus and the emitted electron emerging from the exact same microscopic origin point. To capture this, they utilized a low-pressure gaseous mixture of 40% helium and 60% dimethyl ether. Gas is uniquely suited for this task because it allows charged particles to leave elongated, readable ionization tracks as they move. As the particles ionize the gas, an electric field guides the resulting charge into a microchannel plate. The signal is multiplied inside microscopic pores and recorded onto a pixel chip, where each pixel measures just 83 micrometers across. This coordinate grid illustrates the exact topological signature of a genuine Migdal event. It requires 2 distinct track shapes emerging from nearly the same vertex. The short, compact line represents the nucleus, Because a nuclear recoil deposits energy densely and stops rapidly, its track is blunt and straight. The contrasting track represents the ejected electron. An electron carrying comparable energy scatters through the gas, following an extended, irregular route. To calibrate the detector, researchers fired 2.5 mega-electron-volt neutrons from a deuterium-deuterium generator into the gas. Like the hypothetical dark matter, neutrons are electrically neutral, allowing them to initiate nuclear scattering without ejecting electrons through ordinary charge interactions. Verifying the effect mandates the precise spatial reconstruction of an atom tearing itself apart. A successful measurement requires identifying these specific track geometries rather than simply recording a burst of energy. The primary obstacle in finding these paired shapes is the massive volume of background noise. Environmental gamma rays generate unrelated electron tracks, and multiparticle neutron reactions can overlap in a single detector frame, creating false topologies. To suppress this environmental interference, the researchers surrounded the apparatus with heavy lead shielding, creating a physically isolated zone for the gas chamber. They then applied rigid spatial reconstruction criteria to the data. Out of nearly 1 million recorded events, all the false positives and overlapping tracks were filtered out. Exactly 6 Migdal candidates remained. This graphic illustrates the statistical weight of those surviving tracks. If these 6 events were merely random background fluctuations, the improbability of that noise aligning perfectly into this topology reaches 5 standard deviations, the strict threshold for strong evidence. The researchers then measured the cross-section ratio, confirming a detectable Migdal event occurred only a few times per 100,000 qualifying recoils. Despite relying on a sample size of just 6 events, the physical measurements successfully aligned with the theoretical quantum predictions within the margins of experimental uncertainty. While the data is robust, the experimental conditions have specific boundaries. This test isolated atoms inside a molecular gas mixture, whereas the world's leading dark matter detectors utilize liquid xenon, liquid argon, or solid silicon and germanium. Electrons in an isolated gas atom behave differently than those in a liquid or crystal. Chemical bonds, overlapping energy bands, and immediate interactions with neighboring atoms heavily modify how recoil energy is translated into an observable track. Furthermore, actual dark matter searches require sensitivity to recoil energies far below the 2.5 mega-electron-volt calibration neutrons used here. The effect must be independently replicated across different elements and lower energy thresholds before it can be universally applied. However, the foundational physics have shifted. A detector has recorded the specific paired topology of a recoiling nucleus and electron sharing a microscopic origin. The electron track is not a separate accident following a collision. It is the atom revealing its own internal disruption. By capturing this quantum failure, physicists can finally make invisible collisions visible.